So welcome everybody to our next session in the BME Fractal Geometry Seminar. And I have the pleasure to introduce you Derong Kong from Chongqing University, and he'll talk about open dynamics with moving holes. Please.
So thank you very much for the invitation. Thank Professor Simon and Professor Blanche Ferrani. So it is very great to meet all of you here and wonderful visit. So today I'm happy to talk about my recent work with Beibei Sun and Zhiqiang Wang. So the first is my PhD student, and the second one is my colleague. So in fact, Zhiqiang Wang is now doing postdoc with published work now.
Oh.
Okay, so let's start.
No, I need to. No.
Okay, no worries. So first, let me introduce a little bit about open dynamics. So what is open dynamics? So you have a compact metric space X, and then you have an expanding map T from X to itself. And normally we assume the system has a positive logical entropy, which means it's chaotic. And then you fix a hole we call H. So H is an open connected set. So the question is to look at the set of points X such that the orbit on the T will never fall into the hole H at any time. So the set normally will be a major zero set. So and the size of the set K always depends on the size of H. So when the size of H gets smaller, so the set will get larger. And also it depends on the position where you put this whole H. So there are some, so the first study was in 1979. So Biagani and York, they studied this kind of problem, and they look at the environment measure and give some several topics or several directions on this topic. And later in 1986, so Urbanski, he studied the doubling map on the unit circle with a hole close to zero. So he gave he looked at the Hausdorff dimension of this set KH, and so he also looked at the dimension function when this hole shrinks and how it works. So later, so there are several, so Mark Demas and Lyson Young, so they look at the escape rate and the event measure. So what is the escape rate? So they look at up to time n, so there are still points never fall into the hole. And when this n get larger and larger, so the set of points that they still not fall into the hole H will get smaller and smaller, I mean, in the measure. And the size is getting shrinking to zero when this always exponentially. So they look at the escape rate. You take the logarithm of the measure that the points never fall into the hole up to time n and divide by n. So they call this kind of rate the escape rate. Also, they look, so 2015, Glendon and Sidorov, they look at the doubling map with a hole which is asymmetric somewhere in the unity interval. And the most interesting thing, they look much on the combinatorics on words in this kind of topic. So here I don't want to go much detail about this literature. So another motivation for our study is divergent approximation. So we're giving a positive integer b let TB be the expanding map, X maps to Bx modulo 1 on the intercircle, and you're giving an arbitrary sequence of open balls, Bn. So you look at the set of points that the orbit will fall into this ball Bn infinite many times. So this set is always called well-approximated set. So classical result. So this is also called the shrink-titled problem. But because the center of this BA might not be the same, so it's called something, they have moving centers. So if the sum of this of the diameter BA converges, so then the set W will have the big measure 0. Otherwise, it will have for the bigger measure, you have a 0, 1 lower. So this corresponds to some probability properties. And on the other hand, so if the sum convergence, so this has a 0, the bigger measure, and then it's a natural question to look at the fractal dimension, the Hausdorff dimension, because this set is always dense in the intercircle, so the pattern dimension is not interesting. So the Hausdorff dimension is given for this type of problem was given by Bigon and Bauer in 2014. So they have a precise formula for the Hausdorff dimension of W. Okay, so a natural question. So if the sum divergence, so this means the set has 4 the bigger measure. So what happened for the complement? So the complement will have 0 the big measure. So the question is, what's the Hausdorff dimension of this set? So we call the K be the complement of W. So if there's some divergence, so what can we say about the Hausdorff dimension? Well, of course, in this case, you might also be interested about the packing dimension. So, in fact, this set is not like W. So W is we also call the limit subset. So this one is like the limit if set. So what can we say about this? So we can get some partial result on this. So if the diameter converges to 0, so then the set K will have 4 dimensions. On the other hand, if the set has 4 dimensions, then we can show the diameter BA has a limit if 0. So this is not completely symmetric, but this is what we can get the best way. So in fact, we cannot get limit BN equals 0. So a trivial example is that you just take so when n is even, so you let all this diameter equals to 0, and when this is odd, you let this Bn to be the full interval. So then this set is always so I mean you cannot get the limit if replace this limit if by limit. So this is a little bit awkward. Okay. So then the motivation to study this problem is, so as I said, if the limit goes to 0, then this has a 4 dimension. What happens if it does not go to 0? To look at the things and make it simplify is we look at, so let's suppose the size of Bn to be a constant. And in fact, here we assume this to be all this BA is M level B-adic basic interval. So then the set K can be written as, so for infinite many after, for all but finite many n, so this BA, the orbit will not into this M level B-adic interval at all. So this will be our touch to want to consider. Okay, so now we make these things more precise. So we take B to be bigger or equal to 3. So in fact, when B equals to 2, this is also, some of the results still hold, but there are still some problems. I will explain a little bit later. So let's suppose B to be integer bigger or equal to 3, and dB is our alphabet, and we fix M. M is like the level, and we take D is M block, a block of length M, and ID is B-adic interval generated by this block D. And now I giving a sequence omega. So omega is a sequence of blocks of length M. So each of these omega I is a block of length M. And you can think about each of these omega correspond to a B-adic interval up to of level M. And I define K omega to be the set of points that it will never fall into this B-adic interval at time n. So which means that at time n, so if I look at these things symbolically, so I look at a set of sequence di. Di is a sequence of infinite sequence, and at time n. So if I look at time n, you look at the block of length m. This will not equal to omega n. So omega n is a given sequence that you have already given. And we look at this set. So we call this K omega is a survived set of this open dynamics with a sequence of holes. So the thing is that because this omega I might be different at each time, so the holes, this means that the holes that you have to avoid is dependent on the time n. Okay, so 2 remarks. So if all these omega I are the same, so that means at every time you have to avoid the same hole. So in that case, in the symbolic case, that this will be at n time, you have to avoid a block of length m, which is fixed. So this will give you, in the symbolic space, a subject of finite type. And you do the projection, then you get a graph-directed set. And it also satisfies the opposite condition. So this is well-known result. And another remark is when this m equals to 1. So m equals to 1, so that means you just to avoid a digit. Instead of a block of length m, just avoid a digit. So that means at every time you have to avoid a digit. And these are independent of each other. So in that case, you will get a homogeneous Morang set. So you also have a result for this case. So in the following, we would like to look at the general case. What happened in the general case? So before I go much detail for the set K omega, I would like to give an example to what happened, how to construct K omega in the geometrical way. So I define let B equals to 3 and M equals to 2. So that means you have to avoid blocks of length 2. So I give you omega is 0, 1, which means the first you have to avoid the block 0, 1. And the second, then 2, 1, etc. So I divide the unit interval into 3 parts. And each will give, the first will give digit 0, and then 1, and digit 2. And then I continue. So the k omega says that at time 0, that you have to avoid the block 0, 1. So this means that here 0, 1 will be removed. And all the other length of 2 will be kept. And then I continue. But the thing is here is that if I do look at the second time, so I mean at time 0 you have to remove 0, 1 block, and at time 1 you have to remove 2, 1 block. So that means you have to shift 1 digit. And then in the second case, so that means you have to, so here is 0, 2, 1. So shift the first digit, then you will have 2, 1 here. So this means that this 0, 2, 1 digit block will be removed. And then I continue. So here you cannot see, I mean, there are no interval removed, but here you will get 1, 2, 1. And this 1, 2, 1 will be also, I mean, shift the first digit, then you see 2, 1. So that you have to avoid, and also the last. And then you can continue this construction indefinitely. Then you will finally get a fractal set, a compact fractal set. So it's quite natural to ask what is the Hausdorff dimension, what is the packing dimension, or several other dimensions. Okay, so to state the results, I need a little bit notation. So I defined the adjacency matrix correspond to the forbidden block. So if I give a block D, which has length M, then you can construct shift of finite type with forbidden block D, and then this gives you a direct graph, and which gives you an adjacency matrix. So how to construct the matrix? So it has so the vertex is the set of length m minus 1. So all these blocks of length m minus 1 will be our vertex. And then for 2 vertex, I can construct h from I1 to IM minus 1 to J1 until Jm minus 1. If I can construct and direct h, this means that these 2 blocks are progressively overlapping. So this is the first condition that makes that you can go through one vertex to the other. And also the connected so the connected block of length m should avoid the block D, because you have to avoid this block D. So that's the condition to construct the graph. So here I give an example. So this is m equals to 2. So this means that the vertex has length equals to 1. So then 0 and 0. So there is 0, 1, 2 are our digits. So in this case, 0, 0 is our forbidden block. So which means here this is 0. Now all the other places are equals to 1. So the same for other places. So then the result for the Hausdorff dimension and packing dimension can be explicitly calculated. So the result says for any sequence omega is a sequence of blocks, and the Hausdorff dimension and the lower box dimension are the same, and it can be calculated via by this formula, and the packing and the upper box dimension also the same. So I give a sketch, main idea to calculate this. So one thing is that because this is I look at the b-adic case. So this is each interval corresponds to a cylinder set. So I look at sigma, define sigma k omega is a set of blocks of length k which are admissible, because all of these should be avoid these forbidden blocks. And the size or the number, the cardinality of these sets can be calculated via the product of this matrix. So these are adjacency matrix I just defined. So omega 0 is the adjacency matrix that corresponds to the forbidden blocks omega 0. And then you can continue to do this. So in fact, here is just to count how much passes from the root to the level k versus. So how many passes up to level k? So it's calculated using this formula. Okay, so in fact, from here, it is easy to see that the lower box dimension can be calculated in this way, and the upper box dimension can be calculated in that way. So from this observation, and another thing is to see why the dimension, the Hausdorff and the lower box dimension are the same, is to look at things. So maybe it's better to write a little bit. So the idea is that so this is the root, and then you have several passes. And so let's say this is in level k. So this is our root. And in level k, so the idea tells you that although you have to remove a lot of passes, because some of the passes are forbidden. So then, but still, if I look at the children of this, and also the children of this, and children of this, they might be slightly different up to level, let's say, k plus n. So, the offspring of these vertices up to level n, and also the vertices up to level n here, also here. So these might be slightly different, but they are approximately the same. So it can be bounded by some constant. So there exists some constant which does not depend on n. So when this n gets larger and larger, so it still does not matter. So that's a reason. Finally, you can show the Hausdorff dimension and lower box dimension are the same. Also, you can using this property to show the packing and upper box dimension are the same.
Close the annotation.
Oh, sorry. Yeah, thank you.
Oh,
so I
kept the annotation.
Yeah,
I think that you go back.
Yes, I say.
Just go to the annotate.
Yes.
And
using this one, I can do.
Yes. Yes.
Okay.
application of the Zoom.
Okay. Yes. Okay. Yeah. So now the things is we want to look a little bit more about the range of the dimensions that the Hausdorff and the Pecking can take. So we look at the extreme cases. So one case we call the progressively overlapping. So that means that if we take the sequence omega, so omega is a sequence of blocks, and if these blocks omega 0, omega 1, etc., so they are progressively overlapping. So we have the definition. So probably this definition is a little bit not. I mean, it's a little bit because here is that for OK, so this will be something. So maybe it's better to make a picture for this. I hope not to write too much. Yeah, how to do this. This is the first time, I think. Okay, so let's say, because here is for OK, that suppose this case is much larger, so then you just look at the j between y and -1. So what does this mean? So if I look at, so first, all this omega k is a block of length m. So I have omega k first. So I have this omega k, which is a block of length m. So it will be like omega 1k, omega 2k, etc. So it will be omega mk. So this is omega k is a block of length m, and it says for any j between y and m-1. So here I suppose the k is much larger. So then let's say for j equals to 1, so then you look at the block of omega k -1. So this says, so here I just shift a little bit to the left. So this will be omega 1 k -1 and omega 2 k -1, omega 3 k -1, etc. until omega m k -1. So when j equals to 1, so that means this part, if I use a different color, okay. So this means this part should be the same for j equals to 1. And for j equals to 2, then you go a little bit. So this will be omega k -1. And if I look at omega k -2, so then you will go a little bit to the left. So this will be k -2, omega 2 k -2, and omega 3 k -2, and etc. So this means also for j equals to 2, so this will start from omega 3. So that means also I have to extend this part should be the same. And then you can continue. So of course then you get something finally. So you can continue, and finally this part. So for j equals to m -1, so then the final this will get you something like this. So I just write. So this will omega m, and is k minus m plus 1. So this will give you k k minus m plus 1. So you will have the same picture, something like this. So they are all the same. So this tells you, if I look at the position k, so you have to, at this part, you have to avoid this, and at this part, you have to avoid this. But the block, I mean, the sequence omega is very special. So once you have, so they slightly, a little bit, so this condition is a little bit, I mean, technical. But if I look at this one,
so, do I understand correctly that this condition basically says that if you put after each other the omega, it's an actual orbit
yes, indeed, yes. So that's what I wrote in the different definition. I mean, this means if I look at so this means if I look at this let's say it's omega 0. So you have length block m, and then I look at this is the omega 1. So this is also length block m, but these parts are the same. Mm-hmm. And then only the last digit is different. And then you continue. Then you get omega 2. And also these parts are also the same. So this is like the way you constructed the direct graph. Mm-hmm. So you have this progressively overlapping condition. So in this case, then you will have some extreme. So because these omega are they have much overlap with each other. So then once you avoid one block, then it's more likely you avoid another. So then you have a large chance to get the set to be larger. So this is one of the extreme cases.
So it's not periodic, but it looks like periodic.
Not necessarily periodic. Yeah. Yes. Okay, so probably I need to delete this.
Yes. I think you press the question.
This one?
No, two buttons down. Yeah, that one. Clear all drawings.
Okay. Yes. Wonderful. Thank you. Yes. Yes. So when this omega is progressively overlapping, so all these dimensions are the same. So here I just so in fact you can also write the lower dimension. So in this case, the set is also regular. So that means all these dimensions we studied are the same. And in that case, the dimension can be explicitly determined. So the result says, so in fact, the main idea is the first. So if I look at the size of the kinetic of this sigma k omega, so sigma k omega is the set of these admissible blocks of length k. So these will be approximately lambda to the power k. So this is so you can find some constant c to prove this. In fact, in this case, so you can using the Perry-Frobenius theorem to determine this result. Okay, so here this is why you can get such a kind of I mean why lambda is algebra Pearsall number satisfy this equation. This comes from this recursively result for this sigma k. Yes. So here I don't want to go much detail about how to calculate this, but this is something like you do these things by conditional on position k, and then you look at the other places. Okay, so this is one. So I will tell you later. So this will be the upper bound for all these dimensions for k omega. So this log lambda divided by log b will be the upper bound. So on the other hand, I want to see the lower bound. The lower bound is something just on the opposite way. So I don't want to write detail. So in the progress overlapping case is that you have equal for all these conditions. But now for totally distinct is that for any j they are different. So in this case you will have so that means so when this omega 0, omega 1, and etc. So these are, if I look at the position k, they have a lot of choices. So that means you have to try to avoid the more blocks as you can. So then this means the survival set will get smaller. This is the main idea. Okay, so now the result tells you if omega is totally distinct, then the set k omega is also of the regular, and so all these dimensions are the same. Even you look at the lower dimension, so this is the Hausdorff dimension. So you just look at the local part, the small. If I look at the very sparse part or the very dense part, so the dimensions are the same. So in this case, so the proof is more or less the same, but it's more complicated. So the complicated part is to prove this, because in this case, I mean, although you have similar, very similar recursive equations, but the thing is that not like the previous one, you can using the Parafrobenius theorem very easily. You can find, I mean, the constant c just depends on some Parafrobenius constant. But in this case, it's slightly different. You also need to construct some matrix. But to get this result, the good thing is that, I mean, the matrix does not to act on any positive vectors. You just act on vectors which in some satisfy certain properties. So for these kind of vectors, if I use the matrix to act on this, because this can be written as a product of matrix. So these kind of things, if I, so maybe it's better to write a little bit. Yes. Yeah. Maybe it's okay. So because this sigma k omega, if I look at the size, it will be like the product of these, sorry, some a minus m. So to estimate the size of this, so this means that I have to look at how to using this matrix to act on some vectors. And the vectors I would like to act on will satisfy certain properties. So let me see. So if I write this, because this will be So I just write this as V1, V2, etc. V, in fact, it will be b to the power minus m minus 1, something like this. So I have to act on these vectors, and these vectors satisfy certain properties. So, so this V, if I look at from back to the right, so these will be satisfy certain properties like let me see. Yes, so might be something like this. So sorry, just on the other way around. So will be something like this. So in fact, all these vectors are satisfying certain properties, and then you're using this matrix to act on these kind of vectors, and finally you can show that you can find some constant. So it doesn't matter. It doesn't mean you have to act on. I mean for any vectors, any positive vectors, just act on some vectors on some spatial. Satisfy certain properties, and then finally you can prove this result. Yes. Okay, so
MDX.
Oh, sorry. Yeah. Yes. Okay, so this one means that if omega is totally distinct, I also get off the regular, and later I will show that this will be like the lower bound. And as I explained, because you have distinct arbitrary, as more as distinct options at position k, so that means for the possible choice at position k, you have less choice. So then this means the survival set k that is studied will get smaller. So you have the lower bound, and the result is that if I want to see how much of the regular set that I would like to expect in the for points for the value inside of here, so then I can say a little bit more. So the result says that I can find a dense set inside of this interval that the set k omega is of the regular with this special value as inside here. And also, so in fact, I didn't say much more about, so this L, yes, so this LPQ is constructed in this way. So it's time for k between this j times p plus q, and so if I look at, I divided the whole time into several intervals. So each of these intervals, the first we call the PO interval. These intervals will has length p, and the second will has length q, and I repeat this. So at the first p length p interval, I require this omega to be progressively overlapping. So that means in this part, it is progressively overlapping, and in this part, it's totally distinct. So it's a kind of mixture of these two kind of extreme cases. So in this way, I can show, so in fact, this set is uncountable. So this means that you can find the uncountable many omega such that this set is off the regular, and with this special exponent. Okay. Moreover, so this is as I said, so for any omega, the lower dimension is bigger or equal to log eta divided by log p, and the upward dimension is smaller than log lambda divided by log p. This indeed means that this is the upper bound and this is the lower bound. So the lower bound corresponds to totally distinct, and this corresponds to progressively overlapping. And moreover, for any, if I look at all these dimensions are different, so still you can find uncountably many omega satisfy these properties. And so in fact, I said the dimension for this because it's in the symbolic space. I mean, you can put some, equip to some metric in the symbolic space. And here we just get it is positive dimension, which means that it is uncountable many omega satisfy this property. Also, you can do some multifractal things. So for any alpha beta between this interval, inside the interval, the Hausdorff dimension equals to alpha and the packing dimension equals to beta. So then you can show that this is also, you can find the infinite many omega. So here we found some results from Derong Kong that because the Hausdorff dimension and the packing dimension are related to the product of matrix. So our case, so all these AD, if I look at this AD as a collection of matrices we will study, and these satisfy the irreducible condition stated in the Derong Kong's paper. So in fact, in our case, we just let this capital N equals to 1. So then you will get this is positive. So here it means all the elements in the matrix are positive.
So is the lower bound sharp? Basically, it's the best.
You mean this one? No. So next page, I show you the result. So in fact, then I can use some results from Derong Kong's paper that for any, so if I look at the set of omega, such as the Hausdorff and the packing are the same and equals to alpha. So I define this set as L alpha, and we can show, so well, this is Derong's result. So the Hausdorff and the packing dimension of this set are the same. They can be calculated by the round transform from topological pressure. So, and if I look at my case, the Hausdorff and the packing are different. So then this set can be right as so I look at this L alpha. So the Hausdorff dimension, you just look at the smallest one. So this will give you the Hausdorff dimension. And if I look at the packing dimension, this will be maximum. So this is some results from Derong Kong's work. Yes. So finally, I don't know, is that too fast? Oh, sorry, maybe I don't have much time. Finally, I have some applications for our results. So the first is about the joint spectral radius. So if I give a finitely made matrices have the same size, and so Rota and Judge, they look at the joint spectral radius, so which is defined in the following way. So I just look at the second. These are equivalent. So if I look at the infinite sequence, so this is a sequence, and I look at the matrix, the product along this sequence or along this path. So if I look at the exponent, the diagonal exponent of this product of matrices, so finally I take the supremum among all these infinite sequence. So this will be defined as the Jones spectral radius, which means that you look at the fast or the largest Lyapunov exponent along all these passes. So there is a conjecture by Lagrange and Wang Yang. So the conjecture says for such a kind of real matrix is a finite size. So you can find some finite block such that, so which means this Jones spectral radius can be achieved along a finite periodic orbit. So unfortunately, this conjecture is not true in general. So in fact, in 2002, so Bush and Maricis, so they gave theoretical proof for this conjecture. So they have some very deep theoretical results that this is not true. And 2011, so Kevin Haar, Morris, and Sidroff, and says, so they give a counterexample, explicit counterexample to show that these conjectures is not true in general. So in our case, so if I look at all these adjacency matrix of level, of length m, so then this collection of matrices satisfy the finiteness property. And moreover, we can find the infinite many periodic sequence, because for any periodic sequence which is also progressively overlapping, so then you will achieve the maximum increase. So this is some partial result for this kind of conjecture. Also, so I think I don't know much time. So
no, I think you already paused it a few minutes, but
okay,
maybe 2-3 minutes.
Yeah. Okay.
Maybe 2-3 minutes.
Yeah, sorry. So finally, so for these badly approximate numbers, so I can using the result to give the proof of this, but I think I don't have much time. I think I will skip the proof. So it says if the diameter of these balls goes to 0, so then you have 4 dimensions. The other way you have a similar. So you can using the result what I got to prove this, and also for this Poincare recurrence result. So the thing is that, so we know that almost every point will return to its neighbor infinitely often, and here is a quantization of this result, and they have the Hausdorff dimension depends on the rate. So then you look at the complement of this set, and the complement also has a similar result. If the phi n, the rate goes to 0, so then the 4 dimension, and the other way you get similar results. Yes, so I think I should stop here. Thank you.
Thank you very much. Questions, comments?
So that page you said 1/m is not to advance the lower bound maybe. So and you said you apply results from the gene.
Yes.
So why you cannot get your similar lower bound as the gene, since it has infimum, like
I mean, using that Stringent result, you have explicit the formula, but I mean, it's difficult to calculate the because it's via some implicit formula, so it's difficult to calculate. Yeah. Yes.
There are two questions. One is, so you showed examples of these omega where either all the dimensions were the same, very regular set, or all of them were different.
Yes.
Can you do anything in between, like, I don't know, Hooks and Oslo as the same, but it's different from Hausdorff, let's say?
So we have a result. So the Hausdorff and the lower box dimension are the same for n omega, and also the packing in the upper box are the same for n omega. So this. So that's why I only look at Hausdorff and the packing.
Mm-hmm.
Yeah. So actually, my other question was exactly in this direction, that you gave explicit constructions where the Hausdorff and the packing are the same.
Yes.
This progressively overlapping.
Yeah.
Totally disconnected. Can you give an explicit example where they are going to be different? Because we know the Hausdorff dimension is big, it's bigger than 0.
Yeah. I think we could construct in the proof. So some idea like this. So you choose progressively overlapping at some, I mean, at a length up to n1, and then you from n1 up to time n2. I mean, make this increase very fast. Let this n2 much bigger than n1. So in the next step, you let it totally distinct, and then you continue this way. So I mean, the limit if and the limit sup are different. So
it's kind of like how you make the post dimension.
Yeah. I think in this way you can get the Hausdorff and the packing are different. Yeah. Even one goes to the lower bound and another goes to the upper bound. Yes.
More questions? Did you online people? If not, I have one more regarding the Astro dimension, because in these nice constructions, when there is this possibility of building up this consecutive sequence where you form it in each step, or you are in this very regularly in between, then you end up with all-force regular sets.
Yes.
And then all the dimensions, whatever we can imagine, are coincides. But can you say anything for the Astro dimension for general omega sequence?
Yeah, I don't know. It might happen. They are all equal to.
Yeah, because this
sorry.
This is what I'm wondering. That I
now
don't have natural intuition whether the Australia coincide with the packing, let's say, and the lower is the house of whether I have no good intuition. Yeah. Okay, but
that's a good question, because the Oslo dimension, you look at the set which is a very dense part, and so you look at the local properties of how this set behaves. And I have no idea for a general omega. Yeah, it's a good question. Thank you.
no more questions. Let's thank the audience again. Thank you.